Welcome to another video from Optatube. We're going to talk about something we all use every single second, but maybe don't think about too much. The power grid. It's way more than just poles and wires. It's this enormous, continent-spanning machine that's constantly performing a high-stakes balancing act. Seriously, have you ever flipped a switch and just for a second wondered about the incredible chain of events that has to happen instantly for that light to actually turn on? Well, that's exactly what we're going to break down right now. So, to really get a handle on this balancing act, we've got to start with the basics. We need to understand the physical journey electricity takes, all the way from where it's made right to the plug on your wall. Think of it as a four-step trip. First up, you have generation, where the power is actually created. Then, it hops onto the grid's superhighways. These are the high-voltage transmission lines that cross the country. From there, it gets onto the local streets in a step called distribution, before finally it arrives at our homes and businesses for consumption. And right here, this is the single most important rule of the entire system. You see, unlike water or gas, you can't really store huge amounts of electricity on the grid. That means the amount of power being generated has to perfectly match the amount being used in real time. If that balance is off, even for a moment, the whole thing can fall apart. So if you have to maintain that perfect balance, you need to be a master of prediction, right? Grid operators have to know exactly how much electricity we're all going to use at any given moment. So let's take a look at the demand side of this equation. On a quiet day, say a typical weekend, our electricity use follows this really predictable gentle wave. It's low while we're sleeping, it climbs as we make our morning coffee, dips a bit in the afternoon, and then peaks in the evening. It's got the smooth, pretty manageable rhythm. But what about a cold, dark winter evening? Suddenly, everything happens at once. We all get home, we flick on the lights, we crank up the heat, we're cooking dinner, and now more and more of us are plugging in our electric cars. All that creates this massive, sharp peak in demand. It's a huge stress test that the grid has to pass every single time, without fail. So, how in the world do grid operators decide which power plants to fire up to meet that huge, spiky demand? Well, at the end of the day, it mostly comes down to one thing: cost. They want to give us reliable electricity as cheaply as possible. The system they use is called the merit order. Just think of it like a league table for power plants. They're all ranked by their marginal cost, which is basically just how much it costs to make one more bit of energy. Down at the bottom, with a cost of pretty much zero, you've got renewables. Then come nuclear and coal, and way up at the top are these expensive gas peaking plants, which are designed to be switched on super quickly when demand is at its absolute highest. And this shows you exactly how that works. To meet demand, the operators always use the cheapest power first. As demand climbs, they just move up the list, stacking on the next cheapest source. And to meet that final crazy high peak, well, they have no choice but to turn on those really expensive peaking plants at the top. Now listen up, because this is the part that affects your electricity bill. The price for all the electricity sold in that moment isn't some average. Nope. It's set by the cost of the last and most expensive power plant that was needed to meet the demand. This is called the market clearing price. So yeah, when those pricey peaker plants have to turn on, they make electricity more expensive for everyone. By the way, concepts like the merit order and market pricing are exactly the kind of thing we break down here. So if you're interested in energy market and power system modeling and you want updates and insights about the global energy market, you should definitely follow the Optatube YouTube channel. Okay, we've covered the economics of it all, but what about the physics? What actually happens when that perfect balance is suddenly broken? Let's look at how the grid manages to stay stable second by second. The health of the entire grid can be measured by just one number: its frequency. In a lot of the world, it's 50 hertz. The best way to think about it is as the grid's heartbeat. As long as that beat is steady, everything's cool. But if it starts to wobble, that means the system is in trouble. And the relationship here is super direct. If there's too much generation for the demand, the system kind of speeds up and the frequency rises. If a huge power plant suddenly trips offline, generation plummets below demand, the whole system slows down and the frequency falls. And if it falls too far, you get a blackout. So let's walk through a crisis. At second zero, a giant generator trips and goes offline. Instantly, the grid's frequency starts to nosedive. For that first crucial second, it's pure physics that saves the day, something called inertia. From all the other heavy, spinning machines on the grid resists the change, buying precious time. Then, within 3 seconds, huge batteries can inject a burst of power to stop the fall. By 10 seconds, other generators have ramped up their output, balance is restored. A massive crisis is averted, all in the blink of an eye. That incredible ability to react in seconds is what keeps our modern world running. But the grid is changing fast, and that's bringing a whole new set of challenges and opportunities for keeping that perfect balance. And this brings us to the renewable paradox. On one hand, wind and solar are fantastic because their fuel is free, right? They're the cheapest power in the merit order. But they connect to the grid differently, through power electronics, not with big, heavy, spinning machines. And that means they don't have that physical inertia that has always been the grid's first line of defense. So here's the crucial takeaway. As we transition to a cleaner energy system, we're not just changing our fuel sources. We are fundamentally changing the physics of the grid itself. And that leaves us with a really critical question. How are we going to engineer the stability and the instant response we need into the smarter, cleaner, and perfectly balanced grid of the future?